In this video, we'll try to understand how to find out head loss due to friction. Now this question we have taken from GATE 2012 question paper. Now the problem statement is given over here. Oil flows through a 200 mm diameter horizontal cast iron pipe having friction factor F is equal to 0.0225 of length 500 meter. The volumetric flow rate is 0.2 meter cube per second. The head loss due to friction in meter is, we have to calculate that particular value, assuming that gravitational acceleration g is equal to 9.81 meter per second square. So various options are given and we have to choose the correct option out of that. Now the data is given over here. So d is equal to 200 mm, convert that value into meter. So it is 200 into 10 raised to minus 3 meter or 0.2 meter. F is equal to friction factor, that is 0.0225. Length is 500 meter. Discharge or flow rate, volumetric flow rate is 0.2 meter cube per second. G is equal to gravitational acceleration 9.81 meter per second square, and we have to find out the loss of head due to friction. So according to the equation of continuity, Q is equal to cross sectional area into velocity. So cross sectional area is pi by 4 d square into V. Substitute the value. So Q is equal to 0.2 and diameter is also 0.2. So value of V that we will get is 6.366 meter per second. Now according to the Darcy-Weisbach equation, HF is equal to FLV square upon 2GD. So when friction factor is given, we have to use capital FLV square upon 2GD, and when friction coefficient is given, then we have to use HF is equal to 4FLV square upon 2GD. Now substitute the values of F, L, V, G and D. So F is 0.0225, L is 500, V is 6.366, G is 9.81 and D is 0.2. So value of HF comes out to be 116.186 meter. So in this way we can find out the loss of head due to friction in case of flow through pipe. In this video we'll try to understand how the Bernoulli's equation is applied to the fluid flow. So this question we have taken from GATE 2013 question paper. So problem statement is water is coming out from a tap and falls vertically in the downward direction. At the tap opening, the stream diameter is 20 mm with uniform velocity of 2 meter per second. Acceleration due to gravity is 9.81 meter per second square. Assuming steady inviscid flow, constant atmospheric pressure everywhere, and neglecting surface tension and curvature effect, we have to find out the diameter of the stream is at 0.5 meter below the tap. And the various options they are given over here. So we'll consider the opening of the tap as section 1 and the second section is 0.5 meter below the first section. Now assuming this as a reference, we can say that datum head over here is 0 and datum is 0.5 meter, Z1 is 0.5 meter for the section 1. Now applying the Bernoulli's equation, total head at section 1 is equal to total head at section 2. Now P1 upon gamma, so gauge pressure is 0 at atmosphere. P2 upon gamma is also 0 because they are open to the atmosphere and atmospheric pressure is same everywhere. So gauge pressure is 0 at atmosphere. V1 is 2, Z1 is 0.5, P2 is 0, V2 we have to find out and Z2 is 0 because this section we have assumed as a reference. So this value comes out to be 0.7038 and on the right hand side we are having only V2 square by 2 into 9.81. So V2 square is 13.81 and V2 will be equal to square root of that, that is 3.716 meter per second. Now we'll apply the Bernoulli's equation. So Q is equal to A1 V1 is equal to A2 V2. So substitute the value of A1, that is pi by 4 D1 square into V1 is equal to A2 is pi by 4 D2 square into V2, or if you cancel out pi by 4 from both the sides, then it is D1 square into V1 is equal to D2 square into V2, or D2 square will be equal to D1 square V1 upon V2. Now substitute all these values. So D1 is 20, V1 is 2, V2 is 3.716. So value of D2 comes out to be 14.672 mm or approximately 15 mm. So in this way we can apply the continuity equation as well as Bernoulli's equation to solve the examples on the fluid flow. Thank you very much for watching.